Hello everyone and welcome to my channel. Today we have a question which says that the correct statement about the bond angles of CF3 and CH3 is. So we are being asked about the bond angles of CH3 and CF3 radical and the reason why they are greater than or less than each other. So how we approach this problem? We see that what is the difference between these two radicals? Only the nature of the atoms which is bonded to carbon. So we have CF3 where there is highly electronegative fluorine, and we have CH3 radical where there is hydrogen. So the electronegativity difference between carbon fluorine and carbon hydrogen, so that makes the difference. So you know very well that fluorine is highly electronegative if we compare with hydrogen. So between carbon and fluorine, the electronegativity difference is very high as compared to the electronegativity difference between carbon and hydrogen, which is much lower. Okay, and there are many explanations to this particular problem. So first of all, through VSEPR, we can relate that when we have a very highly electronegative terminal atom, in case of CF3 radical, we have a very highly electronegative terminal atom, that is fluorine. So the terminal atom here is highly electronegative fluorine atom. Okay, this concept is from VSEPR, that when the terminal atom is very highly electronegative, then the bond angle is lower. Now the second explanation, we also know from our knowledge of the free radicals that CH3 is having a planar geometry, while CF3, so CH3 or other radicals like CDR3 instead of hydrogen, if we have deuterium also, and then CR3 alkyl groups attached to the carbon free radicals. So all of these free radicals have a planar geometry. Planar geometry means sp2 hybridization. While when the carbon free radical is attached to a very highly electronegative atom, that is fluorine here, or other examples may include CCl3 or CBr3, so all halogen. When the carbon free radical is bonded to a very highly electronegative atom, the hybridization here is sp3, not sp2. Now we can compare this situation with methyl free radical. So the carbon has 3 sp2 hybrid orbitals, which is bonded to 3 hydrogens through a sigma bond. So there are 3 sigma bonds, and there are 3 sp2 hybrid orbitals of carbon, and the unpaired electron, that is the radical electron, stays in the pure p orbital, which is unhybridized. So the geometry is trigonal planar or planar geometry, and the bond angle is around 120 degrees. So this is the situation for methyl free radical. Now if the same principle is applied to CF3 radical, then what will happen? If we suppose that CF3 radical also has a planar geometry and sp2 hybridized, then what will happen? So you see here that in contrast to hydrogen, fluorine has lone pair of electrons with it. Now what happens? The fluorine's lone pair, fluorine has 3 lone pairs. Okay, fluorine's lone pair shows a significant repulsion with the lone pair on the carbon free radical. And as a result of this repulsion, this bond angle has to be reduced. That means the fluorine and the lone pairs on fluorine and the lone pair on the carbon free radical has to be far apart from one another, okay, to maintain stability. Then what happens? This bond angle has to be reduced to the bond angle of sp3 geometry. Now as you can see, all the 3 fluorine atoms are quite away from the lone pair on the carbon free radical. Now you can see here the geometry is completely changed from sp2 hybridized planar to sp3 hybridized almost tetrahedral geometry. And now together with this, you have to understand that due to this change in hybridization from sp2 to sp3, here comes the effect of percentage S character. So as we proceed, as we progress from sp2 to sp3, the percentage S character is reduced. So sp2 has what percentage S character? So sp2. 1s orbital, 2p orbitals. These combine to form the sp2 hybridized orbital. So in this hybridized orbital, the percentage S character is 33%. While what is the percentage S character for sp3 hybridized orbital? So it is 25%. 0.5% S character. So S character from sp2 to sp3 is reduced, and that is also explained in the books as you read about the difference between CF3 radical and CH3 radical geometry and hybridization. In the books you will learn about the Bent's rule also. So this Bent's rule come from this scenario. So what does Bent's rule say? The Bent's rule says that when the carbon is attached to a highly electronegative atom, or when the terminal atoms are highly electronegative, then the percentage S character of the hybridized orbitals that also reduces to maintain stability. So you can see here why this change in hybridization and geometry is occurring, just to maintain stability, and change in hybridization from sp2 to sp3 leads to a reduction in the percentage S character. Why? Because of the terminal highly electronegative fluorine atoms. So these are the two major reasons why there is a difference in hybridization, geometry and bond angle between CH3 radical and CF3 radical. And so the bond angle is around 110 to 112, not exactly the typical 109 degrees of tetrahedral geometry in case of CF3 radical. So it's around 110 and 112 degrees. So, but it is much less than the trigonal planar bond angle of 120 degrees in CH3 radical. Okay, so you can see one more difference here, that the lone pair of electrons, the unpaired electrons of the carbon free radical in CF3 resides in the sp3 hybridized orbital. So in case of CH3, the lone pair resides in the pure p orbital, because we have only 3 sp2 hybrid orbitals. Here we have 4 sp3 hybridized orbitals, where the 3 sp3 hybridized orbitals, they form 3 sigma bonds with fluorine, and the 4th sp3 hybridized orbital carries the lone pair. Okay, and the actual geometry of the CF3 radical is a pyramidal structure. And also, for a quick recap, why there should be a reduction in the S character? Because of the presence of a highly electronegative element. Now the answer to this question lies in the very basic fact that when any hybrid orbital which is of a lower S character means, and higher S character means. So if it is higher in S character, that means it is more near to the positively charged nucleus. Okay, its electrons are more nearer to the nucleus, that is the S character. Okay, and if it is lower in S character, that means its electrons are further away from the nucleus, that is kind of a, you can say, a P character. Okay, so when there is a reduction in the percentage S character of a hybrid orbital, that means it is moving further away from the attractive forces of the positively charged nucleus. Okay, that means this hybrid orbital with lesser S character has a weaker ability to attract the bonding electrons, since it is far away from the nucleus. And what does this result into? This results into the reduction of the electronegative character. And once the electronegative character is reduced, the repulsion from the neighboring electrons is also reduced. And that is exactly we want in the CF3 free radical. We need the electronic repulsions between the carbon free radical electron and the unpaired electrons of fluorine to reduce in order to gain stability. And this exactly is happening when the percentage S character is reduced for a particular hybrid orbital. So this is the ground story or the foundation behind whatever we discussed regarding the percentage S character and the Bent's rule. So this is the very basic concept. So I hope you have recalled with this particular piece of information whatever you learned in your general chemistry lessons. So now let's move on to the next explanation. Another reason which is given for this kind of lower bond angle in CF3 radical as compared to the CH3 radical is the occurrence of reverse hyperconjugation in CF3 radical. Now we know about the hyperconjugation that you have observed in like ethyl free radical. So there has to be a sigma bond, and the flow of electron occurs from sigma bond to an empty pi orbital. But reverse hyperconjugation, the electron flow is just the reverse. So the electron flows from a filled pi orbital or a p orbital to a neighboring sigma star orbital. So what happens here? This lone pair on fluorine shifts to the CF bonds. So the flow of electron is from N to sigma star. What is sigma star here? The CF bond. The CF bond is the sigma star here. And N is the non-bonding electrons or the lone pairs of electrons on the fluorine atom. And the result is the development of a partial double bond between carbon and fluorine, as you can see here, which donates the electrons towards the CF bond. And a positive charge is developing on fluorine, which donates the electrons. So this resonating structure we can show like this for other two fluorine atoms as well. And here it is important to note that this structure where the lone pair is residing on the carbon atom is the major contributor in the resonating structures, while this one is the least or the minor contributor. Okay. So now if we go back to the question, so we can see here that we have been given four options, and in these four options, first we have to select where there is this option where the CF3 radical bond angle is lower than the CH3 radical bond angle. Okay, so we have option 1 and option 3 where the CF3 radical bond angle is less than CH3 radical bond angle. And then the reason here is due to the N sigma star interaction in CF3 radical that we observed just now in relation to the occurrence of reverse hyperconjugation in CF3. While another reason is given here due to the bond pair repulsion in CF3. No, bond pair repulsion, whenever it happens, it actually, if there is bond pair repulsion, then the bond angle should increase because the bonds will repel, the bond pairs will repel each other, no? And they will be trying to be as far apart as possible from one another. So due to this repulsion, the bond pair repulsion, the bond angles should spread out. That means the increase in the bond angle, not the decrease in the bond angle, because there is bond pair repulsion. Okay, because of which the bond pairs should spread out, and this spreading out should lead to an increase in the bond angle and not the decrease in the bond angle. So this bond pair repulsion should not be the reason for the lower bond angle in CF3 radical. So I hope you understood the explanation, and if you have any doubts you can just write to me in the comment box, and please like, share and subscribe if my videos are helpful to you. Till then, thanks for watching and see you soon.